And so when we look at GIS data here, and this is kind of mean, median, mode, histograms. How do we look at data? Because a lot of times when we look at data, this is what data is. Now, what's the definition of data? I mean to get real kind of deep real quickly here, but what is data?
Information.
Information. All right, it's information. Give me an example of information.
Let's see. Okay. Let's see. So we're looking at
This is obesity
prevalence.
rates. These are obesity rates.
Obesity rates.
Prevalence rates.
Prevalence. So you're looking at, I don't know exactly what the numbers are. There's percentages.
Yep.
And they go by state.
That's just so data would be the obesity rate in Kansas, or Kansas is 35.7. And these numbers here are what we call margins of error. So they could be as low as 34.4 all the way up to 37 based on your sampling size. Because we didn't go and sample every single person in Kansas. We sampled just a percentage of them so we can get a good idea as to what it is. So that's an example of information. And then data is when we put it in a formalized format where we have one column that's state, the next column is prevalence, the next column over here, and we have 95% CI, which stands for confidence interval. And so this is what data looks like to me. You know, it's formalized information in a formalized format that everyone can understand. And me, well, this class, this is what I like to look at. So now we can see these obesity rates here by state. We can see DC is 20%. We can see these yellows are between 25 and 30%. And then we could see where it's darker, the obesity rates are higher. And like I said before, I'm in the where business. I'm not in the why business. And maybe we can go to our health professionals or nursing department to figure out why these patterns exist. Why is it so low in California and Colorado? Low in Hawaii. Why? Any ideas? Hiking, mountains. Maybe food is so expensive, or maybe they tax fast food so much that it makes it cost prohibitive. I don't know. I went to Wendy's the other day. I spent like $10 on a little crappy meal. Ugh, I didn't even like it. And so the why, we'll leave it to other people here. So what do we do with this data? What do we do with the tabular data? Because I can just look at big things in a table and, you know, I can do that. I'd rather look at a map, and then later we're going to talk about all the different things and techniques that we can do with it, because that's part of a GIS, the hardware, the software, the data, the people, the techniques. And this class largely focuses on the techniques. And we're going to talk about some very rudimentary techniques that we can run and what they mean here. And these days, remember in my math class back in the day, I'd have to go calculate the mean and the median using computer. We're just going to talk about what they mean and then figure out how we can extract those. Because at the end of the day, you're going to be a GIS data user. Okay, you're going to be the one, this computer is going to spit out numbers, but if they're not right, you're going to have to be the one that figures out they're wrong. And in my crime mapping class today, we were looking at a crime data set of all 35,000 crimes that occurred in Durham in 2025, represented as a set of points. Now, if I ran a query, this look for the number of homicides, how many homicides do you think occurred in Durham in 2022? Yeah, 25,000. I think it's 36 or something like that. Okay, something like that. And if I were to run a query and it said 35,000, what would you say? Wrong. It's wrong. No? And so things like mean, median, mode. If I were to say, hey, I went and calculated and it said the Panthers' average number of wins per season is 22, what would you say? Oh, that might be 22 over the last 10 years, you know, or, you know.
That's not
accurate. There's only 17. You know, those are the things that we need to really think critically and holistically about when we start looking at things like means and standard deviations. Because I'm going to just throw up the formula here. ArcGIS Pro is going to calculate these things, and especially things called Z values. And Chima can speak a little better to the Z values. We're going to talk about those. And I think they're a real undervalued form of statistics that measure just dispersion and kind of diversity. So what are some things we can do? Within GIS, we can look at high availability versus low availability. I was talking to Jasmine, she's joining us online, where we said, hey, let's look at all the blue dots or the blue squares, the blue polygons versus the red polygons. Is there a difference between those? Or the difference in high COVID versus low COVID? Robeson County versus Cumberland County? Is there a difference in urban block groups versus rural block groups? And I don't want to go down those rabbit holes with what's the definition of urban versus the definition of rural, because I know Chima can answer those questions quantitatively. And so we can go and query these out right here using our GIS techniques. And those of you new to GIS, we're going to kind of learn how to select everything that's, greater than 50 years. And all, what is the cancer deaths, the median age, where it's the age of cancer deaths where they're greater than 50 or less than 30, and the percentage of those. And we looked at those about 3 weeks ago when we were doing this. And you can see a really robust data set that I have here of median age, percent minority. These are by block group. These look like block groups or census tract. Spending on fruits and vegetables, spending on medical care, average number of vehicles. To me, when we start putting together these really robust data sets, they come from a lot of different sources, but this takes a lot of effort to put it together. And these might be the 8 people here that have the best access to food, least access to food. And we can start to run some averages on these. Now later, we can look at the average here, because a lot of times, what do we do this with elections and voting and all that other stuff? These exit polls. All right, 47% of the people voted for candidate A, 45% of the people voted for candidate B. That's the real basic descriptive statistic that we look at. Now, do we know that 47 people voted? Yes, just the 47% of the people that we asked. And then the 43 just that we asked. And so it gets into sample sizes and all those other things, but we'll deal with those later when we look at what we call inferential statistics. So we can measure an entire data set or subset of data, which we do with samples. And so we have scenarios where we look at averages. What's my grade point average? That's a real simple thing here. And then basically, grade point average is, do we just average up A, B, C, A? Do we just average them up like that? No. How do you average them up?
By the numbers, if it's like 3.2.
Yeah, so if you get an A, it's 3. If you get a B, it's A, it's 4. B, it's 3. So we just average up like 4 plus 4 plus 3. Sure. Well, what if I got an F in a 1-credit gym class and an A in a 4-credit lab?
So
That's
Hard to get that F off.
hard to get that F off. Yeah.
In Spanish one year.
Oh.
I went forward to like a 2.9. What the hell happened?
Now, if that's a 1-credit class, that 1 credit isn't going to count as much as the 4 credit. And so it's what we call a weighted average. And we got some examples that we posted in here. How many wins did my favorite football team win in the last year versus my rival over the last 10 years? Oh, it's really hard to like the Panthers these days. I'm trying. I've been here 18 years, and it's really getting really hard. I might have to go back to being a Giants fan. That's tough too. But some more subsidiary questions are, what is the variability in the number of wins for my favorite football team? Do we go from 3 to 14 to 8, 4? Or are we pretty consistent? Hey, do we rather 7, 8, 9, 7, 8, 9, or whatever? And so those get into some of the other more robust or detailed descriptive metrics here. Because a lot of times we want to make kind of beelines for all the geostats and all these other things. But we're going to look at a couple papers today where we just kind of group things. How many? We got urban, rural, suburban. How many are in each? What percentage of people are in each? And so same thing with the SIDS. That SIDS poster over there where we had a former student who was impacted by SIDS. They just said, what's the total number? We're basically, we can see that there's more males versus females that died of SID in North Carolina during that time period. We don't do geostats. We made a nice little map to show where they're highest and lowest, but that has nothing to do with clustering and hotspots and some of the other things that you see in the back, but they tell just as powerful stories, because once we start talking about p-values and ANOVAs and stuff, most of us are going to zone out, but I can make a lot of good information just from that map itself. All right, what's the average COVID rate in North Carolina by zip code? How does it compare to other states? And then what percentage of people live in food deserts in urban regions versus rural regions? And we're going to look at the paper here, and part of reading number 1 will look at that specifically. So we've got measures of central tendency, basically the middle of data, because we're going to look at how data are supposed to be distributed, because next week we're going to talk about the idea of normalizing data. There's a few different ways of normalizing data, but if I were to say, hey, there were 27 crimes in this census or this zip code, there were 37 in this one, well, everyone says, well, 37 has more than 27, but what if the one with what if the one with 27 has a tenth the population? What's that do to the rate? The crime rate goes up. Same thing when we look at death rates. When we map death rates, and I was talking about this with Jasmine, maybe I didn't reinforce my point as much with death rates, but when you map death rates, for leukemia or cancer or diabetes, what are you mapping when you map death rates? What ages of people die at higher rates? Older people. You're just mapping where the older people are. So how do we normalize for that? Now, that's a little bit more difficult than normalizing other types of data. But typically when we look at data, especially the NFL season just started, every team, if you average up all the number of wins, it's going to be 8.5. Okay, you're either going to win, you're going to lose, or once in a while they have some ties here. So you can't have like every team winning 11 games. Why? Because, well, for every win, there's going to be a loser. You would hope. So we've got measures of central tendency, some really easy ones just to describe an entire data set, whether it's obesity that we looked at before. But we're going to look at other things like grade point average, or I think we had some other data on school violence rates and things like that. We have something called the mode. Which one occurs the most? Really easy to calculate. We do something called a summarize on that. We have something called a median, the middle number. Okay, the score or potential score in which it's the middle. Half will lie above it, half lie below it. Then we have something called the mean, or another word for the mean is average. Okay, the average. Okay, you add them all up and you divide by the total number of occurrences. A lot of us think of, when we think of average or mean or central tendency, this is what we look at, but there's other things that we can look at as well. And in some cases, people like looking at the median as opposed to the mean. Why is there, what advantage does the median have over the mean? Is there an advantage? What are countries out there, think of some countries, what are countries out there that have really high median or average incomes? Countries. What are some countries like in the Middle East? Like Saudi Arabia, like Qatar, yeah, Qatar, United Arab Emirates. But, some of those Middle Eastern countries, but what do they have? They have people, workers who make 10,000, 10,000, 10,000, 10,000. What are the people you see on TV? How much they make? 10 million. So when you average up 10,000, 10,000, 10,000, and 10 million, what's that do to the average? Pops it up. What's that do to the median? Nothing, because you're just lining up those numbers and you're grabbing the middle one. And so those outliers, especially those 10 million values, are susceptible, and the mean is susceptible to outliers. Yeah, you're going to hear this word outlier a lot, especially when we do hot spots and cold spots, because by definition, hot spots and cold spots are outliers. They're far from the mean. And so when we start doing geospatial statistics and we say hot spot, it's a high value. What's high mean? Above the mean, no pun intended, or above the average. What's low mean? Below the average. So make sure we know how to calculate something like this. Now we run into lots of issues here when we start doing health mapping and we have a zip code with 4 people and one of them happened to die of cancer and we get a rate of 25%. What if 25% of the people in this zip code died of cancer? That'd be an issue. What happens if 25% of people die in a zip code with only 4 people? It's just kind of an outlier anomaly, all those other things there. It just happens to be one. So we have these like formulas right here. I don't like talking about these too much, but we have this little sigma notation here. I'll highlight this on the screen for our people, this little sigma notation. What does that thing mean? Did anyone remember this from math? Just means add them all up. Yeah, add them all up and divide by the total number. That's all it means. Add them all up. So if we're looking at the average number of Panther wins over the last few years, it's 2 plus 6 plus 3 plus 4 divided by total number of years. Okay. We have median. It's another popular measure of the center. It's denoted by X with a little tilde on top. Okay. And basically, it's the middle. Now, if I have 5 values, what's the middle? Okay, middle, I'm going to put that finger up, but it's going to be the middle, right? Okay, the middle one. Now, if I have 4 of them up, what's the middle of 4? There's no middle there. And so the middle, the median, is going to be the average of the 2 middle ones if it's even. Okay, the average of the 2 middle ones. Now, like I said before, it's resistant to extreme values, but it's not mathematically tractable, meaning that there's no one formula that we can apply for the median. First of all, we got to figure out if it's odd or even. If it's odd, it's just the middle. If it's even, you got to average the 2 middle ones. With the mean, it's really easy to calculate. Now, how do we visualize these? When we visualize data, we have this thing here called a histogram. We're going to look at histograms. We're going to look at some good descriptive statistics here because a lot of our sound work here is based off of descriptive data. Just frequency. What's the word frequency mean? Total number. You're going to look at a map, or we're going to look at some data today in reading number 1 that just has what's the total number of urban block groups versus rural block groups versus suburban. I think it's tracts. Census tracts across, because we're looking at, hey, let's look at urban food deserts versus rural food deserts. But this is a histogram. We can make histograms in ArcGIS Pro. I'm sure you can in Excel, but guess what? I like working in ArcGIS Pro, and we're going to really focus these on ArcGIS Pro because it's going to spit out all of these descriptive statistics in addition to some fancy things. And so we're going to group the value versus the frequency. Now, ArcGIS Pro calls these things bins. Okay, and a lot of times when we look at like the average number of wins by football team, it's going to be somewhere like 7, 8, 9, 10 wins, somewhere in there. There's not going to be too many that win 0 or 1. There's not going to be too many that win 15, 16, or 7. Most of them are going to be scattered in that middle right there. And so when we're looking at frequency of wins versus frequency, you're going to have your higher frequency in the middle. And this is what we call a normal distribution. That's typically how most normalized data looks like. So we have kind of somewhere in the middle right here. In some cases, we have bimodal or multimodal where it's high in the middle, low on the ends. You're not going to have a lot of the 0 or 1 wins. You're not going to have a lot of the 14, 15, 16 wins. In some cases, we're going to have skewed right when we look at raw data like population data. We're going to have a lot of cities with less than 2,000 people. We're going to have few cities with more than 1 million people. And so when we look at population data at the city level or town level, a lot of times it looks like this. So when we start calculating means, medians, modes, standard deviation, it's going to get a little bit wonky when we calculate the standard deviation of all those things as opposed to looking at your normal distribution as well. And so we have descriptive statistics. If I right mouse click on a column and look at statistics, it's going to give us information that looks like this. A count, a min, a max. We know what the minimum means. We know what the maximum means. If we sort them, the one at the top and the one at the bottom, and it gives us the sum, the total. That sum doesn't mean that much to me, like 498,560, but it gives me the mean. It gives me the standard deviation. And so with new ArcGIS, but we're going to be able to open this stuff up, and we can right mouse click. We can just do a screen clip, and we can pop this thing into Excel, pop this thing into Word, PowerPoint really quickly to make this stuff here turn into this stuff here, which is really easy for us to view. And so when we look at something like median household income, we can see it's got a little bimodal for these 64 here. I don't know why this mode exists versus this one here, but you can see it's lower on one side, lower on the other side. That's the extremes here, where the median household income is $80,000 or $14,000, and somewhere in the middle around $40,000, which we typically see for the United States. And you can see the mean, the median, the mode. It's not applicable because you're not going to have a lot of the same values that occur when we have such granular data. So in ArcGIS Pro, we can create histograms relatively easily. So if we look at all 100 counties here in North Carolina, it gives us the mean, the median, the standard deviation, the count. We know what that is. That's frequency. It draws a little line right here for the mean, the median, and then we have this thing here called standard deviation, which we'll visit here in a second. And then has some other fancy things here like skewness and kurtosis. Skewness, basically, in what direction is it? And then kurtosis, how high that kind of graph goes. Is it steep or is it not quite as steep here? But we have these graphs right here, and some neat things we can do is we can click a little export right here, export this button, or these days, I think we might even have a button that says put to clipboard. Pop that thing just like in ArcGIS Pro. You make a map up in the upper right when it clicks share. Put the clipboard. You can pop that thing right into Excel, Word, whatever you want to do, ready to go. And these are relatively new adaptations to ArcGIS Pro. And now I can make a nice, pretty graph that I can insert. I can change the axes, what I call it median age versus frequency, or call it whatever I want to do, and have these ready to go. So there's a lot of examples of normal distribution. Back when I used to play Wordle, does anyone remember Wordle? And so this was kind of my distribution here of Wordle here when I played 120 times. So I had 0, 2, 3, 4, 5, 6. You can see like my distribution of Wordle there. So it took me between like 3, about 4 and 5 times right there. So which I thought was kind of neat or whatever. So another one that I found here, and I like this here, but this is some data that I exported from the NFL Combine. And so those of you who don't know, like for each position every year I think it's in Indianapolis, they have a combine where basically it's just a big meat market for all potential college players where they, do pull-ups and run the 40 and jump a certain number of times. Basically attach quantitative data to each person where they do your broad jump, bench press, vertical jump, 40-yard, height, weight, all that other good stuff. We put them into a little spreadsheet right here, and people like me can basically export these data and graph these, and we can look at the 40-yard time for all of the offensive linemen or whatever. No, these aren't offensive linemen at 4.27, but
for 1 or 2.
yeah, for the running backs or wide receivers right here. But now we can look at a normal distribution or a distribution which we call skewed right of all of the people who attended the combine. And you would think, well, you'd think these are random at some point in time, but you're going to learn in this class, hopefully there's no such thing as random. There's not random. There's going to be a pattern to these. And in this class, we try to elicit the spatial patterns attached to, the geographic data here. But this is what 40 adults running 40 combines make this type of distribution that go from 4.27 all the way up to 5.62. And then we can make these, nice. This is the NFL here. This is the number of wins from the average number of wins from the 2019 to 2020 season. You can see somewhere between 6.8 and 9.7 for the NFL season. So we have a weighted mean. So it's similar to an ordinary arithmetic mean, except that instead of each of the data points contributing equally to the final average, some data points contribute more than others. So now when we go back and calculate your GPA, is that one credit lab that you didn't do well at going to count the same as your 4-credit calculus class. Better not. Definitely does. Okay, so our enumeration units with higher population will contribute more to a weighted average than points with less magnitude. We're talking about this in crime mapping class. We have the House of Representatives and the Senate. How many people are in the Senate? 100. Where'd you get that 100 from?
2 per state.
2 per state. Like I was saying, I took civics for my son and when he was in high school because he knew he didn't want to take it, and he knew mommy and daddy would just do it for him. So
Yeah.
he was just doing it. Because he knew, we wanted him to graduate more than he wanted to. And he knew that. But all kidding aside, is that each state gets to. What about the House of Representatives? 435. Who gets the most? State with the highest. I think it's what, California, 53, and then New York, Florida, Texas, all those other things. So now when we say the politicians going around, are they going to Wyoming and Alaska? No, why not? I don't care.
Nobody out there.
Nobody out there. Do I need my 1 or 2 elected? I don't care. I want California. I want Texas. More importantly, they want state. They don't want California and Texas because those are mainly Democrat and Republican. They want states like Florida and Ohio and Pennsylvania and North Carolina that have a lot of votes, but they can go either way. And that's what they call battleground states. But those are weighted more than the others. So that's what we talk about weights. And so now when I start to calculate, all right, what's the total weight for median household income? I can order these by population. So the 56,000 up at the top counts more than the 40,000 down at the bottom. And so now we can see these right here. We've got FIPS code. These are block groups here. So these ones up at the top that have higher population, they're going to contribute more to the weighted average than those at the bottom. So those higher credit classes are going to count more than those lower credit classes. So make sure in calc or whatever your 4 or 5 credit classes are, you better get A's in those. And the 1 credit class, you can kind of give those up, a little bit. Try to do well on everything. But we have more of a contribution versus less of a contribution. These can be easily done in Excel. And then there's a less of a contribution here as well. Now we got some neat math stuff right here. But basically, if we add up the weights and then we add up the total of your score. Now, think about this when we're doing your GPA. What do you call those? You have something called quality points, right? Yep, that's where those things come from. I call them quality points because I kind of think of that a little bit easier when we look at our weighted average here. So we have our weighted average here where we have the population times the mean, where we have the weighted average and average all of those up. We're going to look at here with our GPA. We're going to do a real quick example here. I'm going to pull some of this out. I want to kind of point our camera over here, just for you all here. I'm kind of going ad hoc here. But we have, you say you had 2 A's, B, and C. You have A, B, C. And this is worth 4, 4, 3, 2. Now, this A, this is a 3 credit class. This is a 3 credit class. This is a 2 credit class. This is a 4 credit class. And so when you start looking at your transcript, what do we see here? We see 12, 6, 8. I got to do math here now. So 24 plus 14 equals what? 24 plus 14, 38. Now, what do I divide it by?
Well, you have to divide it by 8, right?
8 what?
I don't know. Well, there's 8 factors.
Mm-hmm. What do I divide it by?
But OG divided by 12.
So these are quality points. How many credits were I was taking? These 2 credits right here.
Yeah.
Credits. 3, 6, 8, 12. 12 credits.
Okay.
So that's how we calculate your GPA. So 38 divided by 12, which is like 3.2, 3.16. Your GPA. You're sitting there like, hey, I got a couple A's here, but you got a C in the 4 credit class that weights it in that direction here.
Does it all the time.
Does it all the time. So divided by what? The total number of credits here, which is 12. So you're getting skewed here, maybe different words here, because it's weighted more in the C direction than in the A direction. Because if I were just to average these up, if I were to average 4 plus 4 plus 3 plus 2, what's 4 plus 4 plus 3 plus 2 equals to 13 divided by 1, 2, 3, 4
3.
equals 3.25. Here's 3.25 if I were just to average up the grades. Now it's 3.1. Give me 3.25, right?
Yeah. Well, that was my math back in the day.
Yeah, but you didn't count for that. So these numbers, when you look at your transcript, these numbers here, the 12, the 12, the 6, the 8, these are what you call quality points. If you ever look at your transcript, that's what it means. Okay, because it just shows you how to add all those up there. Because these 4, 4, 3, 2 aren't equal. They're weighted, these quality points here. And so this formula kind of shows you those. Now, in the GIS world, we weight them by what? Population. And we're going to look at things called like spatial mean, spatial median, weighted averages. And so when we do the weighted averages, hey, we're weighting that C. If we weight it by that C, that's good. Okay, and so when we look at this weighted mean here, we have the mean of all these numbers. We have the median, which is middle, and then we have the weighted mean, which is $37,000, which is going to be a little bit less here because we have some of these high population areas here that are going to make it go a little bit less right here. So you can start to see the calculation of these weighted. Now, when we talk about quality points and GPAs, well, that makes sense to me here. The same exact thing right here. When we add up all these quality points and then divide by the total number of credits or the total number of population. Now, the other word we have here is called dispersion. What's the word dispersion mean? I know what dispersion means in my house. When I tell my kids it's time to go to bed, all of a sudden they just, I don't know where they went. Just these little footsteps that run in different directions, and but really, all kidding aside, that's what it means. How far it deviates from the mean. So we might have 2 numbers, and I think we have a question on this on the exam is, we have a couple of numbers right here. Someone thought that was funny there. Thank you, Jasmine. You're going to get an A for the semester. She laughed at my joke before about a little dispersion. She knows what I'm talking about. So, but dispersion. So we might have a couple sets of numbers or set of numbers have the same mean, but different measures of dispersion. So we have these descriptive metrics that we have mean, median, mode, some weighted average that we can throw in there. ArcGIS Pro is really good at doing weighted averages, but now we have dispersion, the min, the max, the range. The range is the difference. The range typically is going to be one single number. It's the highest minus the lowest. A lot of times you might hear the term absolute value. We throw in this word absolute value. What's that mean? What's that? Range. If it's positive, make it a negative. If it's negative, make it a positive. And if it's positive, leave it alone. Okay, so absolute value is always going to be a positive number. Okay, we throw those numbers in there. Okay? So a lot of times the range is represented by one number. So we can look at the range of values, the highest minus the lowest between these data here. And those are pretty easy to calculate right there. Now, other things get a little bit more kind of abstract there. We have something called variance, mean deviation. Standard deviation is another thing that we work with where we look at the difference between the value and the mean. And that mean is represented by what we call X bar. Okay. So this X bar is the mean. This is how we start to calculate the standard deviation here. So X is the value, X bar is the average, so this might be 1 minus 10, 3 minus 10, whatever the value is, we go down our Excel spreadsheet because this number is always going to be the same. Okay, descriptive, one value represents the entire data set. Okay. And a lot of times we can do some of these calculations in Excel. This thing is standard deviation. We'll talk about this thing in a second here because we're going to talk about Z values. Z values I really, really like, and I think they're undervalued. Now, to me, all we do is we calculate the difference between the mean, the value, and the mean. We like square it, add it up, and take the square root of it, and that tells us how far it deviates from the average. So if we have a team, football team like the Bengals, who are usually pretty good, but if they win 7 and then 9 and then 11 and then 8 and then the 9, they're really close to the average. So they're not going to, this X minus X bar isn't going to be very high when we square it and then sum it, as opposed to say team that's really bad and then really good and then really good and then really bad. And so when we find the difference between this X and X bar, even though this X bar, which is the average, even though this average is about the same as the Bengals number of wins, these things are highly variable. And when we square them and add them up, this number is going to be a lot higher than the Bengals, which are kind of always around the same. So we can look at some of these numbers as well. So we can do the Excel calculations for the mean deviation, the variance, but to be honest with you, ArcGIS Pro gives us the standard deviation. You can take a really robust math or stats class to go through and do all of these, but I'm not going to kind of waste your time because we went back here, watch this. When we got this, I swear, when I run ArcGIS Pro, look at it, gives me the standard deviation right here, 4.487. Now, what's that 4.487 mean? We'll talk about that in a second when it looks at normal distribution. And so we'll talk about what those things mean there, because we have ways of mapping based on standard deviations, based on our standard deviations. All right, so let me jump back ahead here. I swear, okay. So typically, I like making data in normal distribution that looks like this: high, middle, low on the ends. I use the example of football, or we could look at median household income, average age. I bet you when we start opening up the data and look at the distribution of the average age at which people die of cancer at the county level, I bet you it's going to look something like this. And we can see where it's high and where it's low. And we can figure out the reasons for that. But when we look at normal distributions, typically in a normal distribution, we're not talking about this standard deviation, which is represented, I think this is a sigma, this signal a sigma with the mu right here. About 2/3 of data are between one standard deviation. About 95% are within 2 standard deviations. And about 99 are within 3 standard deviations of data. And the standard deviations are what we start to get into with these Z values here. These Z values here. So a lot of times, I had a friend in college and he had his SAT score disallowed, because he went from like a 900 up to like a 14 or, 990 up to like a 1450. And they said, hey, when we look at the data here, like it's like 7 standard deviation difference between you're starting and ending. There's no way that you could have done this. And you know what he does for a living now? He's a plastic surgeon, and he went to med school, did his master's at Harvard. So basically, he just had a really, really bad day at SATs when he was a junior, and then came back a senior year, studied, and jumped up. But they said, hey, the difference between this is you're over here. Like the chances are a point like 0.0001%, where that, all right, it's a 68% chance because most of the data is going to be here. When we look at football wins with 8.5, most of the teams are going to be between the 5 and the 11. And then you're going to have some more between, the 3 and the 12 or 3 and 13. And then you'll have 1 or 2 teams down here, and another 1 or 2 teams up here. Same exact way. Now, in the real world, they don't make that perfect bell curve shape right here. And so when we look at distribution, sometimes they're skewed to the left. And then I think this is called skewed to the right, where it just kind of trails from this end right here. When we looked at the median age a little bit there. Because the other thing that we have is what we call a z-score. Z-score tells us how far away from the mean something's located. So how far away something's located from the mean. And I'm going to bring this thing out a little bit here in a second here. We're going to have to do some math again. We might do a little physics stuff right here where we work with units. But z-scores make it easy to compare based on different scales. And in geography, a lot of times when we do site selection, I want to build a McDonald's somewhere. Just kind of empirically or anecdotally, if you're building a McDonald's, where do you want to build it?
Populated area.
Populated area. So population, what's that measured in? People? Okay. Also probably high population density. What's the measure for population density? People per square mile? Okay. What about income? Certain income, right? Probably not super high income, not super low income. So how is income measured? Dollars or dollars per year? What about average age of people? Do you want young people, old people? My grandmother's probably not going there.
Middle school, high school.
Middle school, high school. So we want to look at the median age. So you want certain family size too. You don't want a family size of 1. So how do we measure family size? Number of people per family. Can I add up all of those units and it makes sense? Can I add up dollars plus people plus years? Can I do that? It's hard. It's really hard. And so when I start to add up these units here, I'm going to do a little math here. If we have something like 2x plus 3y, y plus 17z, this is how I make my z. But if I try to simplify this thing right here, and I'm just showing the people here, but I have 2x plus 3y plus 17z, where these are the different units. What is this equal to? What does this simplify to? What does 2x plus 3y plus 17z simplify to? This is kind of a trick question, Bonnie, and you already know the answer. You can't. It simplifies to 2x plus 3y plus 17z. So if I have people per family, dollars, distance, people per square, I just can't magically add those up or multiply these and it makes sense out of something. And so I can convert these things to a z value or a z. I'll bring this back in a second here because I'm kind of looking at these things. So when I look at the formula here, a z-score reflects how many standard deviations above or below it is from a raw score. And Sheila's done a really good job at utilizing z-scores, okay, for a particular reason here. So when we do things like site selection, I think it's underutilized, undervalued. Now, I haven't done the research as to why people don't use z-scores, and we'll talk about in a second what it means. But a z-score is positive if it goes above the mean, and it's negative if it's below the mean. And so this is the little formula that we have right here. Z is equal to x minus x bar divided by standard deviation. Okay, because we're going to fill in some formulas right here. I'm going to kind of show everyone right here. Hopefully you can see these or whatever here. But it's equal to Z minus X bar. So now we're working with, say, median age in years. Okay, and I know that for Guilford County over where I live, X, which is the value, is equal to 40.2. X bar, which describes the entire data set, let's just say 37. And then sigma, which describes the entire data set, is equal to, let's say 4.2 years. So my z-score is going to be equal to, all right, 40.2 minus 37 divided by 4.2. Now remember this stuff with our Aunt Sally. Remember that, please excuse my dear Aunt Sally stuff. So we got to do everything on top first. So it's going to be 3.2 divided by 4.2. Alexa, what's 3.2 divided by 4.2? You guys do that?
Yeah.
I do that. Alexa, where are you? What are you doing here? Why have you left me at such, what's that?
0.76.
0.76. Alexa has left me. Okay, 0.76. Okay. What are the units for 0.76? I know Chima knows. Don't look at him. Don't look back.
So what are the units?
What are the units? Okay, because
So we were looking at years.
so this is years.
Yeah, we're looking
We
at
got years in the top, years in the bottom. What happens to these years? They cancel themselves out. So what is it? Nothing. So 0.76. So it's unitless. So now instead of working with years, what if we're working with people per family? What happens to people per family? Cancels out. What happens to dollars per year? Cancels out. People per square mile, what happens to it? Cancels out. So the value of it is that the units cancel out. So when I say 0.76, that means it's 0.76 standard deviations above the mean versus the income, 0.72 below the mean, 3.2 above the mean. And so when I go back to this graph here, when I look at a standard, what's going to be a really, really high standard deviation? A real high standard deviation.
something over 95.
Okay, that percent.
Oh,
2, 3.
2, 3.
Okay, so when we start calculating, if you get something like 7 standard deviations, it's really, really high and really, really rare. Okay, so when we calculate these by hand, somewhere between -3 and +3. Okay, so similar.
But -3 would put you below the distribution, which would be.
Yeah. All right. See you guys. So it'll put you really high because when we start running our statistical tools for randomness dispersion, we might get c-values like 27. That means it's really far over here, which means there's intentionality with it. Really, really high. Okay. So the last couple of things, I like the z-score because it's unitless. And so now, hey, let's get a z-score. We're going to do our site selection for McDonald's, and our z-score for our income is going to fall, it's going to be an acceptable z-score, okay, around our mean. Average family size, population size, income. When we add up all these z-scores, that's going to mean something more to me than adding up all these unitless or these united values. So what we'll do here, we're going to take a 10-minute break right